the hafnium oxide typical epsilon or K value is like 20. And the silicon dioxide, we just said, is like 4. So that means 1 nanometer silicon dioxide equals to how thick hafnium oxide? Any idea? What's the ratio here? 5, right? So that's the ratio, okay. If you want to convert. So this is the relationship. Okay, so here is a chart for different high K dielectric materials. There are two properties of the material. One is the band gap, one is the dielectric constant value, this epsilon. So of course we want higher K value, and as I said, silicon dioxide actually is very bad in terms of the K value. It's only like 4 here. Many other materials have higher K value. However, there's a trade-off. So with higher K value, for example, here titanium dioxide, TiO2, maybe have 80 dielectric constant. The band gap is only like 3 point something or 4 eV electron volts. Silicon dioxide is like 9 electron volts. So what does that mean? That means with those higher K value, the leakage current will increase. Because if you look at the band diagram between the two electrodes, this is band diagram, okay? This is like silicon dioxide. You have this band gap, which is like 9 eV, very large. So electrons very hard to jump over. So that's a leakage current through the capacitor, right? So if you use higher K value, yes, the C is larger, but also at the same time, then you have more leakage current. I leak will go up. So this is not good, because you know DRAM, we care about the retention, right? Then if you have too much leakage current, then the retention will be bad. So that's why here I think industry choose somewhere in the middle as a trade-off or balance kind of design. So that's why the zirconium oxide, hafnium oxide is typically used for the DRAM capacitor. Question?
Do they sometimes use, say, a compound stack, like so many, if they make it, often our heterostructures, so you have some silicon dioxide and then some hafnia.
Yes.
To sort of play between the leakage and the dielectric constant?
Yes, I think in today's DRAM is not pure zirconium or hafnium oxide. So, but what alloy or what exact composition is the secret of those companies. I don't know. Yeah.
Why does the band gap and dielectric constant have this kind of?
Oh, that's a good question. That's by nature. I don't know. Yeah. The material property is just like that. Question?
Does that 6 electron volt region mean something in the boundary? There is a boundary kind of a thing at 6 electron volt. Does that mean something?
Oh, you mean here? I don't know. So why in this have two corners? Yeah, so but basically this is a kind of optimal space. Any other questions? Okay, so this is in terms of the material. So this is probably zirconium, hafnium oxide, or the exact composition. I don't know. So this is the structure of the capacitor, the shape of the capacitor. There are two kinds of shape. One is called the cylinder type, the other one is called pillar type. So here, this is how you make the structure. let's say those two electrodes. For example, this black one is let's say the storage node where you connect this to the transistor's source or drain. So this is one electrode, and then this kind of orange is this dielectric, this insulator, and then the other side, this white space is a plate electrode. So one structure is something like this. You have this kind of storage node, and then fill in the dielectric, and then this plate in the middle. So in this case, the diameter, let's say this diameter of this capacitor is the thickness of this, twice of this thickness of this storage node, plus twice of the thickness of the dielectric, and then in the middle you have this plate diameter. So this is the total diameter for this structure. And these days, I think industry is switching from this cylinder type to this pillar type to simplify this structure. So in this case, the key dimension here will be this dielectric, this let's say dielectric thickness plus the plate diameter. So in this case, you simplify this a little bit. So this will allow you a little bit better scalability of this kind of structure. So here it shows the technology trend. Let's say from 70 nanometer down to 20 nanometer here, like a cylinder capacitor, and then below 20 nanometer is like this pillar capacitor. And here this is I think this is aspect ratio we need to maintain this CS. But still, even with these innovations, the CS is shrinking these days. But the aspect ratio here, you see that used to be like 10, but now below 20 nanometer, it approach like 100. So what does this mean, this aspect ratio? You can see this is very tall, and then this diameter is so small, and this aspect ratio is height divided by that diameter. So it's very hard to make this kind of structure from manufacturing point of view. And you need an EOT like 4 angstrom or 3 angstrom. So this is extremely difficult these days. So here are some images for the stacked capacitor. So there are some problems because of this aspect ratio too high, right? You know, it's like this pen is standing up here. If this pen is very high, then you know it may fall down, right? Due to this very high aspect ratio. So we do have this kind of problem. For example, here are some images of a failure in the product. You see here under the microscope, you see two capacitors just clap. And this is a mechanical stability problem. So at the 20 nanometer technology node, I think the industry introduced this mechanical support layer. So you see here, because this is so tall, then in the middle, so somehow they have something, I don't know what's there, but they have something to mechanically support this very tall capacitor, preventing them from being falling down. So again, this is some data showing the trend of the aspect ratio and with the technology node. for example, at 90 nanometer node, the aspect ratio is only like 10. But for today's, like this is 20, around 20 nanometer, it's already 80. But today, it's already below 20 nanometer. So you can imagine that maybe 100, above 100. And the dielectric, they switch from aluminum oxide to zirconium oxide, and this is EOT, I think 6 angstrom for 20 nanometer. And yeah, this is as you mentioned, Anthony has mentioned. So it says multi-stack, and they don't disclose what's that. So, and the capacitance actually is really shrinking these days. And as I said, 25 femto is a typical value, but we really cannot support this. So you see this value is still kind of shrinking over the generations. So this is the trend of the capacitor. It's really difficult these days. That's why not many companies can produce the DRAMs.
So for the pillar type, does the cell size change? Because my storage node is now it's not on top of the capacitor anymore, right? The contact. So does the cell size, like, does the real estate on silicon change? Like, do we need more space?
Do we need more space? Actually, that's a good question. I'm not so sure how that is actually. So I think this, you still need to have some space here. But you can shrink this. But this storage node, you still need some space here. I don't have the data for the numbers. What is the typical number? Yeah, unless you have the TM image, someone reverse engineer the sample and then take an image. Otherwise, very hard to get those numbers.
How do they make the contact?
Contact. This one is still connecting to the transistor. Yeah, we don't have an image showing this, so I don't know the exact connections.
We know how does it influence those high aspect ratio like DRAM process?
So what process?
Like which kind of process do they make that high?
So that's a good question. So I think of course the capacitor, the insulator, the dielectric is done by ALD for sure. Yeah. So and the electrode, I'm not so sure how to refill the plate. Let's say the electrode material.
So all these technologies, it seems really won't disclose anything about how they make it.
Yeah, maybe they will say something, but personally I don't know. So they may have something somewhere. I didn't check. But for sure the dielectric is done by ALD. This is for sure. Yeah.
Will it be similar to last time the NAND device? There's one time the lecturer introducing some NAND fabrication by Samsung.
Which?
Because they also have a very high aspect ratio of like
NAND flash.
NAND flash.
NAND flash is yeah, it's different. So NAND flash is a little bit different. But as long as that, let's say dielectric deposition into that trench or that pillar, that one for sure is ALD. Yeah. But the middle, this inner electrode, how to do that, I'm not so sure exactly. Yeah.
I think his question is about the etching. So let's say if you want to pattern the electrode,
Yes.
now how do you maintain that high aspect ratio
Oh, etching.
without it cracking or breaking?
Yeah. So etching, that is by the stretch, and that's how the applied material make money. Okay. So those equipment companies are really making the money out of those etching tools, especially from the 3D NAND. 3D NAND is even more difficult than this one etch, because this one is you just etch the same material. Let's say you have the dielectric, and then just dig some hole into that dielectric. 3D NAND, I think the next lecture, or we may revisit this later. 3D NAND, you have the metal dielectric, different materials in that stack, and you want to etch through different material. That's even more challenging. This is why you only have one material to etch. So, yeah, so those are the fabrication challenges. And then let's look at the Bitline capacitance. We talk about the CS, okay, but the sense margin, Bitline capacitance is also the key factor there, because we care about the ratio, right? Not only CS, but also CB. So if you look at the component of the Bitline capacitance, you can have different contributions. So because here the Bitline capacitance, there are many contributions. This is the transistors, Bitline contact. So this Bitline will have capacitance everywhere, right? For example, here from Bitline to Bitline, this number 3 is Bitline to Bitline coupling, because in between Bitline you will have the dielectric to separate the Bitlines. So this is like a parasitic cap. And then the Bitline to the storage node capacitor, because this capacitor is standing up. So then the Bitline to that capacitor will have the coupling cap. And then the Bitline contact, here is a contact. Contact here to the gate, and this is like drain or source contact. Then here you will have spacer, and then you have the parasitic cap. And then the Bitline contact to the substrate. So you see there are many kind of contributions to the Bitline capacitance. But here if you break down that, mostly is like this Bitline to Wordline cap. So it's this guy, number 1. And this is because this spacing is really small. The distance is very small. The capacitance, if you have smaller distance, the larger capacitance. And then number 2, this one. Those two contribute most to the Bitline capacitance. So, any ideas to reduce Bitline capacitance? Although we talk about that over generations, then this Bitline capacitance does not scale too much. But still you can find techniques to reduce that.
They use a low epsilon interlayer dielectric.
Yes, so this is exactly opposite to what you want for the CS. Right? For cell capacitance, you want larger capacitance, you use high K material as the dielectric. This one, you should use low K. That means low for those insulator between, for example, between Bitline or from Bitline to Wordline, so the spacer. So all of those materials need to be low K. So what is the lowest K value you can get?
K.
Yes, 1, which is like a vacuum or air. Air is close to 1. So this is exactly what industry is doing. So you look at this. So this is a cross-section image for that. So this is a storage node, and this is a transistor, I think. Oh, sorry. This is a transistor. Where is the transistor? Let me see. And I think here is somehow this is a transistor. And then this is the Bitline contact to the storage node, which is this number 1 here. And here the spacer, is air spacer. So basically you put nothing there. You need to etch out that space and make a void there. So then you can have the lowest K value. So this is already introduced in 20 nanometer load technology. I think this is first introduced by Samsung at 20 nanometer node.